Hello again. Welcome back. We are now going to discuss periodic table of the elements part 2. So let's see what's on the agenda today. The topics that we will discuss are the Bohr diagrams, the Aufbau principle. German word Aufbau means build up. Electron configurations and orbital diagram. The meaning of a core noble gas electron configuration. Energy diagrams, the Hund's rule of degenerate orbitals, which is discussed in atomic theory as well, isotopes and nuclide representations as symbols, atomic number, Z, coming from the German word Zahl, and the atomic mass, which means A for us. The atomic mass unit, the AMU, that is the unit when we compare relative masses of the elements to a certain unit, which is the AMU. The relative isotopic abundances and calculations of average masses or percentage distribution of the isotopes in nature of a given element, and the meaning of valence electrons, and the octet rule once again. Here we have the energy ladder, so to speak. Let's start from the bottom, from the innermost shell, which is the K shell, as you remember. So I'm going to go down. And we look here and see the lowest possible energy level is the 1s orbital. Remember, we can have 2 electrons in one orbital. Every one of these circles represents an atomic orbital. Of course, we have different types. This is all discussed, of course, as you might know, in the atomic theory part of this course. And we have the 2s, which is the s level of a higher shell. So the spherical orbital is a little bigger. It's almost like a Russian doll system where each consecutive s of the higher shells enwraps all the inner orbitals that might occur as we go upward towards the outermost shell, which is the 7th shell. Beyond that, we have ionization. Notice that the gaps get smaller and smaller. This was reflected in the electronic spectra of the elements, especially hydrogen. And we have then in the L shell, remember that's the 2nd shell, 2n square rule means 2 times 2 square is 4 times 2 equals 8. So we have a total number of 8 electrons that can be housed in the L shell. So we fill up the electrons according to the energy level. Like when you go up a staircase, you don't skip certain steps. Normally you wouldn't, unless you're maybe 3 years old or something like that. So we go step by step, gradually up the ladder and fill the orbitals with electrons. That means each consecutive element will add 1 electron to the whole setup. So hydrogen would have a 1s type of electron configuration, and helium would be 1s square, meaning 2 will be in the s orbital. And we can go through every element this way, and as you see, the p levels start occurring in the L shell, on the 2nd major shell, quantum number n equals 2, and according to Hund's rule, remember, we can only fill what we call degenerative orbitals with 1 electron each before we double them up to the normal counter spin duplets in each orbital. So this would be 1, 1, 1, and then double, double, double. That is Hund's rule of maximum multiplicity. Then we go on to the 3rd shell, and we have the same thing. We don't have d orbitals yet that are filled up. Because remember, we have the octet rule. The octet rule means even though we can theoretically have more electrons, as long as the shell is the outermost shell, it is called the valence shell, and the limiting number is 8 electrons. So that means even though we can have 3D levels, we have to open up a new shell, which is 4s. And you notice also that the 4s level is lower than the corresponding 3D level. So of course it's going to be filled up before, when we stick to our rule that we go by successively increasing energy levels, the normal staircase. So the 3Ds will be opened up after the 4s, and that means the transition elements will start coming in and completing unfinished business by filling up the third shell from 8 to 18. So 10 elements must follow suit, each one consecutively putting an electron in one of these degenerative d orbitals of the third quantum number, main quantum number, meaning the main shell. And then we go on. Once the 3Ds are finished, we continue with the Ps, and then we round up that outermost shell again with 8 electrons. That means we have reached the noble gas that sort of wraps up the valence shell with 8 electrons. And then we start over again with the next higher shell. 1, 2 electrons come in. Those are the alkaline, earth alkaline main group metals. And then we go backtracking again so that we start with the d orbital of the fourth shell. And when we have also the possibility of having F levels, then nature does it in such a way that you put 1 electron here in the d set, and then you go on to the 4f, which that means a 5d, and then you go back down to the 4f levels and complete them with from 10 to, from 18 to 32. So the inner transition elements are the ones that complete the shells, the third to the last shell, from 18 to 32. So everything is done in piecemeal fashion, and then we continue upwards. And notice that the levels get closer and closer together. It gets a little fuzzy here up at the top of the staircase, and eventually the steps get smaller and smaller, and in the end you have no more distinct quantized energy levels. You have randomness, and that's no longer the atom. That means we're out of the vicinity of the atom. Now let's just look at this diagram that relates to the element radium. So radium is a pretty heavy element. It is an alkaline metal. It has 88 protons in the nucleus, and the mass number is 226. We call this the nuclide representation, where the lower left number is telling us what atomic number the element has, and the top left-hand number is the one that tells us how many total nucleons are in the nucleus, including protons and neutrons, and that would be our mass number. So we have here this beautiful curve that shows us how symmetrically the the main shells are filled with electrons. So you start with a little, then 8, then 18, then 32, then back to 18, even though we could theoretically have 50 here, and then we go sort of back down. So it's a nice little equal distribution. And the alkaline metals have a perfect symmetry in their orbital diagrams. Here on the bottom, we see the Bohr diagram. And the Bohr diagram just lists the electrons as they occur, similar to the planetary system. So we don't break the electrons down into their sub-energy levels. We just use them completely, like 2, 8, 18, 32, 18, 8, 2. That would be the electron distribution in the main shells. The electron configuration, on the other hand, will break these electrons down into their proper compartments, meaning the sub-energy levels, s, p, d, and f orbitals. So this doesn't tell us in what orbitals the electrons are. It just tells us the total number per shell. Now we can also use the so-called core noble gas to save the trip of writing every little orbital down, because every new element has sort of an inner complete noble gas electron configuration. And then we can just use a bracket with the element, and any extra electrons will be put on the side with their proper electron configuration notation. Okay, let's look at here the radium again. This is how the electrons would be built up. This is the energy profile diagram, this whole thing. And we start from low to high. We go from low to high. So here we have two arrows with opposite spins. Remember the Pauli exclusion principle. That means we cannot have the same quantum numbers of two electrons, or the electrons have to each, within one atom, have to differ, cannot have the same set of quantum numbers. They must at least differ in one. So these two electrons have all the same except the last one, which is called the spin quantum number. And so they have to have opposite spin, meaning rotate in the opposite directions when they go around their own axis. So here we see how the electrons are systematically filled. And remember Hund's principle, that the electrons are first singularly filled and then doubled up when they are on the same energy level, which we call degenerate orbitals. So since the radium is an alkaline, earth alkaline metal, it has the valence of 2. That means it has 2 electrons in its valence shell. So it can make 2 positive ions. Everything else is full, so it's a completely filled up system. And we can use a core noble gas to represent the inner electrons. Here it shows how we go to higher energy levels. I'd like to now talk about the famous AMU unit. The AMU unit stands for atomic mass unit, and it has been established by chemists per definition as having the actual mass of a carbon-12 isotope atom, for which we can establish the real actual mass. It happens to be 1.9927 times 10 to the negative 23 grams. And when we divide this by 12, then that number is supposed to be what we call the AMU, the atomic mass unit. So the atomic mass unit stands for this mass. And we really have the unit grams. So it actually is, or practically is, the unit of one nucleon. The nuclear building particles, the particles that make up the nucleus, as we have established, are the protons and the neutrons. So they have almost the same mass, only the neutron is a little heavier than the proton. It's almost like a proton plus an electron together. So this has been decided to be the AMU unit. So any other element is a multiple of this AMU. Actually, it would be the mass of one hydrogen, roughly speaking. So we can say that the relative mass of carbon is 12 AMU, because we took its original mass divided by 12 to get the AMU. So to get back the real mass again, we just have to multiply that factor by 12 again to get the actual mass. But we don't want to use the actual masses in everyday calculations. We just stick to the relative masses. The coefficient is the actual thing of importance here. But if we really want to get back to the actual mass, we can do that, because we just have to remember what the AMU stands for. So the relative mass, or the atomic mass of carbon, would be 12 AMU, but we usually don't say AMU. We say 12. We also have what we call the molar mass, which is 12 grams per mole. So that is also the same coefficient again. So usually the AMU is understood, but not written. Now, one thing that we have to talk about here too is the isotopic masses, because most elements have isotopes or exist as a collection of different isotopes. That means they have the same atomic number because they belong to the same element, but they have different number of neutrons. So therefore the mass numbers differ. And we use a nuclide representation to indicate this. So we have here, for instance, 2 copper isotopes. They're both copper 29 because that's the key number that determines copper, the atomic number 29, meaning 29 protons in the nucleus. But the number of neutrons vary. In this case, we have copper 65 has 2 more neutrons than copper 63. So it should be slightly heavier if we would put it on the scale. Now, we know the relative abundance of copper. We know that the copper 63 is more abundant than the copper 65. It's almost a ratio of 70 to 30%. So how can we establish the average mass? We just have to take the absolute masses in AMU, the coefficient, the relative masses in AMU of one isotope and the mass of the other isotope, multiply it by the percent. That means we move the decimal 2 spaces to the left and say 0.70 times 63, calculate. And we do the same thing with the other. And then we just add these numbers, and then we get the so-called average mass. And look, I calculated by rounding the number 63.6, and the real literature mass of the average is 63.55. Those are often the masses you see in the periodic table. They already represent averages of various isotopes. Now let's look again at the Aufbau principle, or the build-up principle. Let's say the valence shell in this scenario is the 5th shell. Then it always has to be filled with 1 or 2 electrons so that it is considered really a valence shell. And then when we have unfinished business still to do, then once we have some pro forma electrons in the outermost shell, the valence shell, then we can go back down and fill up the shell to its needed amount. We always do it stepwise. So the previous shell, we also always build up from A to 18. That means 10 electrons are needed here. However, when we have lower shells that need to be brought up to from 18 to 32, then we do a little trick here. We fill up the second to the last shell with 1 electron and then go back down and make sure that the lower shell is brought to the proper amount, meaning from 10 to 18. And once all this is done, we can complete always the above shell to what it needs to be. For instance, once this third to the last shell is completed with the F electrons, or the 18 to 32 electrons, then we can go back to the transition metals that will complete what they originally started with 1 electron, which would be at first lanthanum. So lanthanum is not an inner transition metal, it's a transition metal. It just opens up the possibility to go back down to the third to the last shell. But once this third to the last shell is completed, then we continue with the second to the last shell to the proper amount, which we call A to 18. That means actually it would be 9 to 18 now, because we already had one initially in there. What is valence? Valence is actually how many electrons an element can share or exchange. That means donate to somebody else or receive from somebody else. So remember, the elements more on the left of the periodic table make positive ions. The middle group, the carbon group, is plus minus 4, so it's neither nor, sort of smack in the middle. And then we have the negative valencies, the negatively charged ions that result from the exchange of certain electrons. So you see, we again have a nice little regular symmetry in this distribution. The octet rule we already mentioned is always the outermost shell, or refers always to the outermost shell. That means the outermost shell, regardless of what normal number it should or could have, has to be limited with 8 electrons. Now we have these exceptions, as I mentioned. The first shell cannot have more than 2. And we do have sometimes the possibilities of elements that are in the higher period, in the higher periods 3 and onward. They have some empty d orbitals in the previous shell that they can use for expansion of the octet. So they can sometimes have a decade or a dodecad, meaning 10 or 12 electrons. This is what we call octet expansion. The Bohr diagrams, as I've already mentioned, It's just a listing of the electrons in the various shell. Here we have carbon with 2 in the innermost shell and 4 in the valence shell. Now if we want to break that down and want to know what kind of electrons are they, then we do the so-called electron configuration, and that would be 1s2. That means we have 2 s electrons in the first shell, then we have 2 s electrons in the second shell, and 2 electrons in the p energy level of the second shell. And remember, the parallel spins in separate orbitals is important because of Hund's rule. Remember, degenerate orbitals are filled separately before they are doubled. So if we want to break it down, then we have 1 electron in the 2px orbital that is on the x-axis, and 1 electron is in the 2py orbital on the y-axis. The 2pz orbital is empty. Now what would be the core noble gas? It would be helium. So I could just say helium, 2s2, 2p2 for the electron configuration. And here we see it in more detail. Now I'd like to talk about a very interesting experiment that was carried out by Moseley, who produced X-rays. And these X-rays can be produced easily with a so-called modified cathode ray tube. So the glass blower made a certain bulge in the tube because it needs what we call an anode that has a slanted surface. And it has to have a big surface, and it's made up of a certain material that we want to study. So the cathode rays are bombarded onto the slanted surface of that metal, the counter electrode, which is the anode. And interestingly enough, electrons that collide with matter release electromagnetic energy, which is highly potent, and we call those X-rays. They have the similar energy to the gamma rays that are natural in our environment. So X-rays are artificial in a sense, and these X-rays can be analyzed by spectroscopic methods. We send the rays through a prism, and the rays are diffracted in this prism, and then we get the lineup, the emission spectrum of particular lines recorded in various means. Now when you observe or study these spectra, it turned out that the atomic number is a function of the wavelength. So when you did a little transformation, you could line them all up here on the line. All the elements have a certain position point on this line with a certain slope. Now that is pretty regular, I would say. So that reinforced the periodicity idea of the periodic table. That means the properties are a function of the atomic number. Now here we have the idea that Moseley used. Every little spectrum that he found for different materials, mainly metals of course, he lined up, and he could see that certain lines represent certain atomic numbers. And I have this here in a real spectrum. Before we look at that spectrum, let's look at Moseley in his laboratory. He was a relatively young man, and he made tremendous headway in the study and the understanding of atoms. And here we have what we call an X-ray photoelectron spectrum of neon. And you could see that the electron energy and the ionization energy, the top scale is the electron energy in joules, and the bottom scale is the ionization energy. So we have the photoelectron spectrum, how much energy is needed to ionize these electrons. Here on the lower right, we have what I just talked to you about. the overlay of the various line spectra of the X-rays produced in his modified tube. So these metals were used as targets for the electron beam to hit, and the X-rays that were produced gave a spectrum like any type of light. And you see the only mixed compound or substance in this case is brass. We sometimes have 1 or 2 lines, sometimes more lines, but with this buildup you could relate atomic number to wavelength. And that's what Moseley determined, and that's why we call it the Moseley law. And with this, we conclude this part of the episode. The periodic table took a long time to get established. The important thing was that we have decent, workable atomic mass numbers, or atomic weights, as one used to call them. And with that, people could play around and see if there's any periodicity involved. So many people were just playing around with these numbers, and they noticed certain consistencies and irregularities. And one led to another. It took a long time for the periodic table to really be accepted. Many people were skeptical, or they thought everything was just a coincidence. So people had to fight uphill to get the periodic table as it is established today. Now the numbers, as I said, increase consistently because people in certain laboratories where they use cyclotrons can bombard atoms with fundamental particles and get new elements. And hope you enjoyed this episode, and goodbye until next time.